In this video lecture, we are going to be trying to find the moment of inertia for a particular bar. Bar are going to be the rod by using the bifilar suspension system. This is one of the methodology we are using to find out the moment of inertia for this type of bar, either rectangular bar or circular rod we are going to be using. So how we are going to be find out the moment of inertia for particular bar? So in this case, I have taken the bar that's going to be the A, B. So then I was suspended to the two flexible strings I have taken. In this case, that's going to be A, B is going to be the bar, and the fixed point C and the D I am going to be taking to the frame. So then what happened is that the flexible strings. So then the length of this one is going to be the L we are going to become. So then in this case what will happen? So A and B are going to be the total bar we are taking. At the same time, the weight of the system is going to be acting through the center of the gravity that I am going to be taking. The point is going to be the Z acting vertically in the downward direction. So in this case, when the weight is going to be acting in the downward direction, then these two are going to be the flexible strings. That's AC and BD is going to be the flexible strings. They are going to be acting. That means the reaction force are going to be developing, and that's going to be trying to pull in the upward directions. So that I am going to say TA and the TB are going to be the tensions in the flexible strings. So then what happened? This weight is downward direction, but the tension is going to be acting in the upward direction. So here I am going to be writing the TA and the TB are the tensions in the strings. AB is going to be the what? A bar or a rod we are going to be saying. So then G is going to be the center of gravity point, and W is going to be the weight of the bar. So and L is going to be the length of the string, that is going to be the flexible string. So in this way we are going to be, first we are going to be finding the tensions in the strings TA and the TB. Those are going to be the flexible tension strings we are going to be calculating. So if I am going to draw the free body diagram for this case, so then what will happen? I am going to be considering this is going to be the bar AB. So then what happened here? The center weight, that is going to be weight of the bar acting vertically in the downward direction. So then what happened? This spring tension is going to be acting in the vertical direction, and this one is going to be acting in the vertical direction. So that's going to be TB and the TA. The distance between point A and the G is going to be the L1 distance, assume, and here is going to be the L2 distance, it is there, right? So the same distance I am going to be taking here is the L1, and here is the L2 distance we will have. So then how would you calculate the TA as well as the TB? And we know that we are going to be applying the summation of the moments acting at a point is equal to 0. That I am going to be taking sigma MA equal to 0, and similarly sigma MB is equal to 0. When I am going to be taking the moments at A, so that I can calculate the TB value. When I am going to be taking the moments at B, I can calculate the TA values. So I am going to take the moments at A. So that's going to be sigma MA is equal to 0. That's going to be, so in this case what will happen when I am going to be taking the moments here? This is going to be acting in the clockwise direction. This is TB is going to be acting in the counterclockwise direction. So that's going to be, what is the distance between TB and here the perpendicular distance? That's going to be L1 plus L2. That is going to be TB into L1 plus L2. So this is the distance that is equal to, because it is moving in the counterclockwise, this is moving in the clockwise direction, that's going to be the distance is equal to L1. So then I am going to be writing TB is equal to W L1 plus L2. So we do have, this is the equation for the TB. This is the magnitude, the tension is going to be, you can say, in terms of the newtons. So then once we calculate the TB, then I am going to be calculating the TA. That's going to be moments at B is equal to 0. So in this case also, what will happen? This is moving in the clockwise direction, this is moving in the counterclockwise direction. So that's going to be TA L1 plus L2, that is equal to W into L2 distance, because the perpendicular distance to the self weight and to this one is going to be the L2. So that I am going to be taking TA is equal to, what is the formula? That's going to be WL2 by L1 plus L2. This is the magnitude, we got the tension. TB is equal to, this is the tension, and the TA, this is the magnitude, is existed here because of the self weight of the system. This way we can calculate the TB as well as the TA. Once we are going to be calculating the TB and the TA, so then what I am going to do, I am going to give the small displacement to the bar. So that's going to be, so this is going to be the bar in this direction. So then what happened? I am going to be giving the small displacement in the horizontal direction. So once it is going to be moving, automatically these flexible strings also will change its deflection. So that means it is also angular displacement is going to be taking place. So then what is here that I am going to be taking? After you are giving the small displacement, that means small force I have applied over here. So then it will come to the new position. So this is going to be the new position. I am going to say this is going to be the A dash and this is going to be the B dash. A, B is going to be the initial position, A dash and B dash is going to be the new position. It is making an angle theta, and here also it is going to be making an angle theta. So then what will happen? So it is going to be, this position is going to be the A dash and this position is going to be your B dash. Okay, so then the string is going to be taking the deflection from there. That's going to be like this. So this is the deflection position, and here also we are getting the deflection position. So the string with the vertical position, it's going to be say pi 1, and this is going to be the pi 2 angular displacement it has taken by the spring. That means the string. So from here we are going to be calculating the restoring torque. So we need to calculate the restoring torque. The restoring torque is equal to the that's the total restoring torque is equal to the individual restoring positions we are going to be adding. So in this case, the vertical component is going to be consist of TA, and similarly after the displacement it's going to be shifted to this position, that I am going to say the A dash, and this is going to be the A, and this is going to be. So here in this case what will happen, and this is going to be the C, and here it is in the vertical position. That means once it is going to be shifted to the new position, that's going to be the pi 1. So then it is going to be clear, this vertical component we have resolved into two components. One is going to be the horizontal component, one is going to be inclined to that. So then what in this case? So in this case the pi 1 value is going to be, that is angular displacement of these strings are going to be very less compared to the angular displacement of the bar. So then what will happen in this case? The acceleration also going to be generating at the string as well as in the bar. So in this case also, once again in the comparison, the magnitude of the accelerating or the restoring time is going to be more in the bar compared to the strings. The strings are generating the very less restoring force compared to the bar. So that we are going to be neglecting the accelerating force due to the strings are going to be neglected, and only we are going to be considering accelerating force by the bar. So then how we are going to be calculating this component? So then in this case what will happen? I am going to be taking the force component in this case. This is the TA, and this is going to be the A dash is the horizontal component. So that I am going to say AA, horizontal component HC1 if I am going to be taking. So then how could you calculate the HC1 if I am going to be taking? Because this is the opposite side to the angle. Then I am going to be writing sin pi 1 is equal to, what is the formula? Opposite side is going to be the A1, right? That means A dash divided by the vertical component, that's going to be the AC. So then A dash, that is equal to sin pi 1 is equal to, so here AC is equal to how much? TA. So then sin pi. Assuming that the sin pi 1 is going to be the very small value that I am going to be writing, this is going to be HC horizontal component for this TA. So that is equal to TA into pi 1. So this we got it. And similarly, in this case what will happen? This is the one side of the center of gravity point. Other side also is going to be acting. The restoring force, how it is going to be acting? It is going to be acting in this direction. This is going to be acting in this direction. So by the combination of these two, then it is going to be generating the restoring torque. So then how could you calculate the horizontal component? So here is the horizontal component in this direction. So that I am going to be drawing. This is the point D, and this is the point B, and this is going to be the new position after the angular displacement. Then I can say the B dash, and this is going to be the pi 2 value we can say. So how could you calculate this horizontal component? Because what is the acceleration force is going to be generating because of the string that was neglected. Only the horizontal component accelerating force is going to be generated by the bar only considered in this case. That I am going to be taking sine pi 2. So this is, we know that PB. So that is equal to, opposite side is going to be the B dash divided by, so that's going to be BD. So B dash is equal to, what is the formula we do have? BD is equal to TB into sine pi 2. And further simplification, I can say horizontal component 2 is equal to TB into pi 2. Alright, so then we got it, the horizontal component for this position and the horizontal component for this position also. So once we are getting, when we are trying to find out the pi 1 and the pi 2 values. How could you find out? The same diagram I am going to be taking. This is the force component we have taken. But what is the total length of this one? That's going to be L is there. So how could you take the L over here? So that I am going to be draw once again the diagram. So in this case, first case I am going to be taking this one. This is going to be your C and A, right? And this is going to be your new position is the A dash. And this is going to be the G point is there, and it is going to be passing through this one. It is making an angle theta, and this is the L1, this is the L distance is there, and this is going to be the pi 1. So in this case what will happen? In the triangle of AC A dash, in this case common, that's going to be A dash is going to be your horizontal component. In this case also, AG A dash. In this case, A dash is going to be the common side for these two triangles. When I am going to be have these values, then I can going to be equating. So in this case, what I am going to be getting, that's going to be sine pi 1. In this case, the triangle AC A dash. Suppose sine pi 1 is equal to A dash by AC. I am going to be getting A dash is equal to AC is equal to how much in terms of the geometrical properties? That's going to be L into sine pi 1. So in this case, sine pi 1 is going to be the very small value that I am going to writing A dash. This is the horizontal component. So this is the triangle. I am going to be taking AG A dash. So then triangle AG A dash. So then what is the formula? Sine theta is equal to, the sine theta is equal to, opposite side is going to be A dash divided by hypotenuse, that's going to be the AG. So then in this case also A dash is equal to, AG equal to how much? L1 sine theta. So then A dash is equal to L1 theta, we got it. Right? In this case I am going to be comparing these two, because A dash is going to be the common in this case, that I am going to be getting, that's going to be here L pi 1 is equal to L1 theta. Pi 1 is equal to how much? L1 theta by L. So then once we are getting the pi 1, then I am going to be substituting in this equation. So then the pi 1 is equal to formula L1 theta by L. So in the same way, what is the theta 2 pi 2 value? So if you are going to be taking this one, so this is going to be the D, and this is the B. This is the new angular position beta dash. Okay, then in this case, it is moving in this direction. This length is going to be the L2, this is the L, and this is going to be the pi 2, and it is making an angle theta. Right? So then the same value I am going to be getting, the pi 2 is equal to L2 theta by L, we are going to be getting. I am not deriving here. With the help of this one, we can also find out this one. The pi 2 is equal to L2 theta by L, we got it. So this way we got the pi 1 and the pi 2. So then after we are going to be calculating the restoring torque. As we know that the restoring torque is equal to force into the radius distance we need to take it. So we know that this is going to be the old position, that is going to be the initial position, this is going to be the new position. So that I am going to show with the dot X. So in this case what will happen, there is a TA, and we know that the TA pi 1 is acting here, and in this case what will happen, TB pi 2 is going to be acting. So then what is the distance between here? L1 and this is going to be the L2 distance. As you know, the torquing force, one is acting this side is going to be. From this point, both are going to be in the circular direction. That's going to be total restoring torque. Total restoring torque. What is the total restoring torque in this case? That's going to be total T is equal to TA. So this is the tension acting here. That's into L1 plus TB pi 2 into L2. So this is the force, horizontal component force is acting towards this side. It's trying to bring back to its position. That's why we are going to be taking the restoring torque. What is the TA? The TA is equal to, what is the formula? W L2 by L1 plus L2. What is the phi 1 is equal to? L1 theta by L, we got it. And here is the L1. So right, plus, so what is the TB? TB is equal to W L1 by L1 plus L2, and the pi 2 is equal to L2 theta by L, we got it. That's going to be multiplying with the L2. So after the simplification here, can you see here, in this case, W is the common terminology and theta is the common terminology. L1 L2 is going to be the common terminology. So that L is going to be the common, that is going to be L1 plus L2 also common. So that I am going to be taking to the one side, so that I am going to be simplifying this equation. So that's the T is equal to W L1 L2 theta by L1 plus L2. So in this case, once we are going to be taking, and finally we do have L1 plus L2. We do get, and here is going to be multiplying with the L. So then the finally L1 plus L2, this is going to be the cancel. The final restoring torque T is equal to W L1 L2 theta by L, we are going to be getting. So this is going to be the restoring torque. From this restoring torque, we are going to be substituting in the accelerating torque. Accelerating torque is equal to, what is the formula we do have? T is equal to I alpha we do have. So from this case, we are going to be calculating the moment of inertia. First, initially we are going to be calculating the alpha, then we are going to be calculating the I. Then once you substitute it, you will get the I value. So as we know that this is going to be T is equal to the accelerating torque I into alpha. We got it the restoring torque, and I is equal to the moment of inertia, that is equal to m into k square. In this case, we are using the W, that I am going to be writing W by G into k square. In this case, we need to calculate the k square value. So once we are going to be k square value, so that easily you can find out the moment of inertia. So then alpha is equal to, so alpha is equal to, this is going to be the angular acceleration. That's going to be T by I value we are getting. What is the T here? So that's going to be W L1 L2 theta by L, we got it. So then what is the I value? That's going to be W by G into k square we do have. So that I am going to be simplifying. So then what happened here? The G is going to be the top position, W into k square we get it. So then I am going to be cancelled out any value here. W is going to be cancelled out. So from this equation, we are going to be getting the alpha. So that's going to be alpha is equal to G L1 L2 theta by L k square we got it. So this is going to be the angular acceleration of that component. So as we know that the angular acceleration alpha is equal to omega square by theta, angular displacement we do have. From this one we do have the alpha. So that omega square is equal to, what is the formula we are using? This is going to be the G by, it's going to be alpha by theta. Alpha is equal to G L1 L2 theta by L k square into theta. So theta will going to be cancelled. Then omega square is equal to angular acceleration G L1 L2 by L k square. So this case, from this one we can calculate the k value. So that's going to be k square is equal to, what's the formula? G L1 L2 by L into omega square. So this way we have calculated the k value. Once your k value is there, then we are going to be substituting in the I. So right, so that I is equal to m k square we do have. So right, m k square, m is equal to, already we know that W by G, k square is equal to G into L1 L2 divided by L into omega square. G will going to be cancelled out. The finally from this equation that we are getting, I is equal to W L1 L2 by L into omega square. So this way we are going to be calculating the I value. As we know that the bifilar suspension system is one of the experimental method, so that we can calculate the moment of inertia. So any complicated shapes of these bars also easily we can calculate the moment of inertia.